In the previous episode, we talked about big O notation, and I said that algorithms are basically the problems that you want to solve, and the toolbox is the data structures. Today, we are going to talk about our very first data structure, and that is an array. So let's jump right into it. This is an array in Swift. There are two types of arrays in Swift, actually, a static one and a dynamic one. By default, Swift has dynamic arrays. Let me just talk you through what that actually means. When we are storing an array inside memory, it allocates a certain space in memory for that particular array. If this array is declared as static, you cannot expand on it. It has 7, 3, 5, 6, 2, 12, and 4. You cannot actually add more. That other next element, memory slot, might be actually used by something else. That is one thing to know, because in memory, an array is contiguously stored, meaning that the compiler will find a memory slot long enough to store all of this data. So it will be one after the other, which is really great because then lookup is quite simple, not that memory intensive. That's why we have indices. An array is an ordered collection, which means that order really does matter. So 7 is the first, 3 is the second, 5 is the third, and so on. Now, how do we access it? Well, through the indices. So the first, we access it by its index. Now, in programming, the first index is at index 0. Now, if you're not having a background in programming, this might be a little bit confusing. But just so you know, we're not starting the indices from 1. We are actually starting it from 0. So 7 is at index 0. 3 is at index 1. 5 is at index 2. And so on. Now, that is a static array. But in Swift, we actually are using something by default. We're using a dynamic array. Now, what does that actually mean? Well, if you think about it, when you want to append, let's say, a new element to a static array, we don't have that luxury to just add the next element to the array because it's capped in memory. The next memory slot might have something else, a string or whatever. So it's limited. So when we are trying to append to a static array, we are going to copy out all of the array, add the new element, and the compiler will just search for a new memory slot, a lot of memory slots, that can hold this new array. And that is O of n of time complexity, which is really expensive, because we are going to go through each and every element, put it into another array, and then also expand on it. So O of n, and also O of n of space complexity, because we are creating a new one. So to avoid this, there's something called a dynamic array, and that's what actually under the hood Swift has, Swift arrays have. So think about it like this. When we are creating a new array, something like this, we are actually not having, let's just have these with 0, so I'm not going to have any warnings. I'm going to paste the zeros right over here, all of them, and maybe remove the 0 and make it 2 over here, so it's quite understandable. So think a bit, when we are allocating some memory to this array that I highlighted, actually under the hood, the memory is much longer, actually double the size. So these slots, they are not occupied. They are just waiting there for to be occupied. So whenever I want to append a new element, let's just say right over here, I just add maybe 50, then it will be a time complexity of O of 1, so constant time complexity. It will be instant because the memory slot is already available. Now, that can go all the way up to whenever the double is expired. And if we want to add even more, only then we are going to actually copy out and do that, O of n complexity work on the array. And then when I'm going to copy this out, let me just paste it in there and add a new one, all of these zeros, these will be just 0, 0, 0, 0, 0, 0, just to have the new elements added, available over there. That will expand the array even on a doubly basis. So again, just so we have inserting at the end of O of 1 time complexity. And whenever we reach, again, this end, and we want to expand on it, it will double in size, double in size, double in size. So yeah, that's what dynamic arrays are. And for this particular feature of it, in many cases, it's even more performant than, let's say, linked lists, because we're going to talk about linked lists and time complexities and all of that in an upcoming episode. But think about it: whenever we want to jump to the next element on a linked list, we're just going to search through another place in memory, and then another place, and then another place. This is contiguous, so you're just taking up one block of memory. That's where it's really, really fast to just come up, access all of these elements. So let's just go through all of these. Accessing the time complexities. Accessing is O of 1. We just say, I want element at index and whatever. Index 1 or 2 or 0. And it's instant. Updating. I'm not going to go through the syntax. We are going to go through a lot of syntax when we are going to get into the actual algorithms. For now, just the theory. Updating is the same. So we just access the number index and we just override it. O of 1. Inserting at the beginning. Now this is interesting. This is O of n actually, because what do we actually want to do? Well, let's just add 0 over here and some other zeros. But if we want to add, let's say, I don't know, let's just have 9 at the beginning, we are going to actually shift every element by 1. And we need to go through each and every element to just shift it. I know we already have a spot available in memory for the last element because we just shifted 1. But we still have to go through each and every element. That's why inserting at the beginning is O of n. The same goes inserting in the middle because of the nature of time complexity. We are just basically cutting O of n by half in the middle, but dividing by a constant in terms of time complexity, it doesn't really matter, still O of n. Inserting at the end. Now, this is really interesting. Inserting at the end is O of 1, so constant time, if the array is a dynamic array, and for all the purposes that I talked about when I explained dynamic arrays. And this is not always the case, because when we got to that last element of the allocated free memory and we still want to add some more, then it again will be of O of n time, but O of 1 amortized. So in general, this will be O of 1. So that's great. It's just going many times it will be O of 1, and once it will be O of n, and then it's just going to double in place again. So O of 1 amortized. And then if this is an actual static array, then it's definitely O of n, because we don't have this functionality of storing or reserving rather memory slots for upcoming insertions. Okay, so that's why O of n is also right over here. This is amortized, so not pure O of 1. Removing at the beginning. Now, removing at the beginning is still O of n, because we are going to remove the 9 over here and then move the 7 instead of it, in place of it, 3, 5, 6, 2, and so on. And we still need to go through all of the elements of the array. So all that. Removing at the middle, same thing, O of n, because, it's just how time complexity is calculated. Now removing at the end, it's really, really nice because that is O of 1. You know, if we just want to remove this one, we can access it through its index. It's just, removing it and nothing else. It's just fine. So O of n. Copying is O of n, because the reason I told you also previously, when we are copying, we are going to go through each and every element of the current array, and we are going to place it in a new array. So O of n, n time, n meaning the number of elements inside the array. And also, fun fact, this will also have O of n space complexity.